All right, today we're going to dive into a really clever trick that your computer uses to supercharge data transfers. We're talking about direct memory access, or as you'll always hear it called, DMA.
You know, it sounds kind of crazy to say, but when it comes to moving huge amounts of data, your super powerful CPU can actually be a real bottleneck. See, every single moment it spends just shuffling data, byte by byte, is a moment it's not running your programs. It's like using a world-class sprinter to deliver mail one letter at a time. I mean, sure, they can do it, but what a terrible waste of their talent, right?
So if you're studying computer engineering, especially in a program like the one at Gujarat Technological University, this concept is going to be front and center in your operating systems course. The whole subject is really all about one thing: managing system resources, like the CPU and memory, as efficiently as possible.
And a huge piece of that puzzle is what we call I/O management. The big question we're always trying to answer is, how does the OS get data from, say, a disk or a network card into memory without grinding the whole system to a halt?
Okay, so to really understand the solution, we first have to appreciate the problem itself. And that problem is having a totally overworked CPU thanks to what I call interrupt overload. Let's look at the old way of doing things.
The standard method is called interrupt-driven I/O. So imagine you're downloading a huge file. With this method, every time a tiny little piece of data arrives, the I/O device basically has to tap the CPU on the shoulder with an interrupt signal saying, "Hey, got another byte for you, come and get it." Now, for large transfers, this is just wildly inefficient. You're moving a gigabyte file, that's a billion shoulder taps. The CPU has to stop what it's doing, handle that one byte, and then try to get back to its real job, over and over and over again. It's a massive, massive waste of valuable processing time. So how do we fix this mess? Well, we do what any smart manager does. We bring in a specialist, and this is exactly where direct memory access comes into play.
DMA is a separate, dedicated piece of hardware. The best way to think of it is like a highly skilled logistics manager that lives inside your computer. It has one job, and one job only: moving big chunks of information from point A to point B, all without bothering the boss, the CPU.
So how does this whole process kick off? Well, the CPU doesn't just step aside randomly. It delegates the job properly. It creates what you can literally think of as a work order and just hands it off to the DMA module.
This work order has 4 absolutely critical pieces of information. First up, are we doing a read from a device or a write to it? Second, what's the address of the I/O device we're talking to? Like the hard disk. Third, where in the main memory should this data start being placed? And finally, exactly how much data are we moving? How many words need to be transferred?
And once that work order is handed off, we get to the real payoff of using DMA. We get to build a much more efficient system through something called concurrency.
With just those 4 simple instructions, the CPU has told the DMA everything it needs to know. The CPU's part in this big data transfer is now basically done. It can go off and do something way more useful.
And here's the real magic, the core benefit. The DMA module takes complete control, and it transfers the entire block of data directly between the device and memory. It completely bypasses the CPU. So while the DMA is busy being a data mover, the CPU is free to go execute another program. They're working in parallel. This is true multitasking, right at the hardware level.
But wait, what about all those interrupts we talked about? The constant shoulder tapping? Well, DMA has a very elegant solution for that too.
Instead of sending an interrupt for every single byte, the DMA module just waits. It works quietly and efficiently in the background, moving that whole block of data. It's only when the entire transfer is 100% complete that it sends a single interrupt signal back to the CPU.
Just one. One single notification that basically says, "Hey boss, that huge gigabyte file you asked for, it's all here, safe in memory, right where you wanted it, job's done." We're going from billions of interruptions down to just one. I mean, that is an absolutely massive gain in efficiency.
So, let's just put it all side by side. With standard I/O, the CPU is basically a stressed-out micromanager, getting interrupted constantly for every little thing. With DMA, the CPU is a smart delegator. It gives one command and gets just one notification back when the entire job is finished.
Now, for anyone studying for GTU exams or the gates,
Listen up, because this is the key takeaway. If you remember absolutely nothing else from this, remember this distinction. It's the difference between overwhelming the CPU with constant tiny requests versus freeing it up with one smart delegated task.
And this all leaves us with a final thought to chew on. We've seen just how powerful DMA is for these big data blocks. But that kind of begs the question, right? If DMA is so much better, why haven't we just gotten rid of the old interrupt system completely? Why do our computers still need both? Something to think about. Thanks for tuning in.